So now we switch gears and we look at the data structure that have very fast query but with high storage. To start with, as it's a simpler problem, we look at the half space range counting. We have endpoints in the plane. The query is a half plane, like this, or the query is the region of the plane below a line L, and we want to count the number of points inside. Okay, so the first thing we do is to dualize. Remember that we want to count the points that are below this line L. When we go to dual space, the points become lines and the line becomes a point. Since we want to count every point that is below the line, it turns out that we want to count the number of lines that pass above this query point L. Okay? So now this problem is actually very easy to solve. What we can do is to build the arrangement of these n lines. The arrangement has n squared size. And for every cell in the arrangement, we just write down how many lines pass above it. Okay? Then we build a point location data structure on all these segments. So this means that given a query point, so this takes n squared space because there are n squared disjoint line segment in the arrangement. Remember that to build a point location data structure, you need a set of disjoint line segments. But you have n squared disjoint line segments over here. The query time of a point location is the log of the input, so it's going to be log of n squared. But log of n squared is basically 2 times log n. So that means the query time doesn't change asymptotically. The query time of point location is still going to be log n. And in log n time, I can find which cell of the arrangement contains my query point. And of course, here conveniently, I have stored how many lines pass above it. So therefore, I could easily count the number of points in the dual problem. How many points are below this line now? That gives you n squared space with log n query time, which is very nice. Okay. So this is a very nice solution, but it's very limited in the sense that we still are interested in more complicated questions. So for example, can we report the number of points in log n plus k time? What if instead of having a half plane, I have a triangle? I want to count the number of points inside a triangle. So now we're going to look at those solutions. To answer those solutions, we need to use the cutting lemma. The cutting lemma tells you the following. You imagine that you have a set of lines in the plane, and we're given a parameter r. We can partition the entire plane into roughly r squared triangles with the following properties. That the number of lines that intersect every triangle is at most n over r. And this is known as the conflict list of every triangle, and it's denoted by this. So I'll give you a pictorial example. So let's say this is the set of lines that we have in the plane. And I build this decomposition of the plane. So I cut my entire plane into this many triangles. Of course, here some of the triangles are unbounded. Let's say like this or like this. Actually, my picture is slightly wrong because this is not a triangle. So I guess I should do dot here. So essentially you have these regions that have 3 edges in them. I guess this is also not a triangle. Okay. So you cover the plane with roughly r squared triangles. The property of these triangles is that when you look at every triangle in the picture, it is intersected by at most n over r of the input lines. The cutting lemma shows the existence of such covering. We're not going to prove it. Again, the proof is beyond the scope of this course, and it requires a PhD level course to do it. Okay. So now we can solve half space range reporting. In other words, if you want to report the number of points inside the half plane. The way we do it is very similar to we use partition tree with. We build a 1 over r cutting, where r is some large enough constant. Okay. For every triangle in the cutting, I store the list of lines that pass completely above this triangle. Then guess what happens? We recurse on the set of lines that intersect the triangle. That's the data structure. Okay. let's analyze the space. R is a constant, so there are R squared triangles. In the worst case, all the lines pass above the triangle. So therefore, storing the list of lines that pass above every triangle takes at most R squared times n space, and since R is a constant, that's in linear space. So that means the recursion for the space becomes something like this. We have R squared triangles. Each triangle is intersected by at most n over R lines. So whenever I recurse on the set of lines intersecting every triangle, that is at most n over R lines over there. So we have R squared recursion of size roughly n over R. And at the top, at every recursion step, I spend linear space or R space. Okay. So that's essentially an easy analysis. What does this solve? So again, in the exercise class, we're going to solve that. We're going to show that this solves to roughly n squared plus epsilon space. So the space is almost as claimed. It's roughly quadratic. What about the query time? So now, given a query point, we want to find all the all the lines that pass above it. This should be above. Okay, right. I changed the typo in the slide. So we want to find, given a query point, the set of lines that pass above it. So we find a triangle that contains my query points. Let's say this green triangle. Well, I have stored the list of lines that pass above this, so just report them. Then I need to report the set of lines that pass above this point, but those that intersect this green triangle, so just recurse. It's a very simple query algorithm, and it's also very easy to find a recursive formula for this. So ignoring the time that it takes to report things, you essentially have this kind of recursion, and actually this should be R squared. Let me quickly fix that as well, because I have R squared triangles. So I look at every triangle, I produce a list, and otherwise I recurse. And the thing is here, the difference here is that I only recurse on one triangle. So when it comes to recursion, I have only this. I have only n over R, the size of my subprogram that I recurse on. And now you can see this is, you don't need exercise class to analyze this. This solves to log R. Technically it solves to, R squared log n, because at every level of the recursion, I'm doing R squared work. But since R is a constant, it is absorbing the own notation, so it just analyzes to log n.